Okay, well, welcome back to our course on system engineering. Our last lecture, we just gave an introduction to the general subject and the textbooks that we're using. And now we're going to get into the details. And like I said, we're going to be using the format, the structure of what is laid out for the textbook by Booty. And so this is the three sections that Booty has in his textbook. And so the first section is an introduction, overview, and some basic knowledge of what system engineering is. There are a couple chapters on discrete mathematics. And so for some of you, this may be a review. For others, this may be new. And I will give an introduction to this, and this will be something that you can be considering and how you may be using that in your future in terms of system engineering. The second is going to be the section on design and integration. And so this is going to be going through a linear process per se of going through the whole design and development and also the integration of a system design. Plus, then there's going to be some supplemental topics. And this is another reason why I think Booty is noteworthy for us to be thinking about it, including this last chapter on the value of system engineering. So for today, we're going to be doing this introduction to system engineering. So what we're going to cover is we're going to define what a system is. We're also going to be considering what system engineering is, which if you're talking to somebody that has no idea what it is, it can be fairly challenging. We'll be talking about the life cycle of a system, and then we'll be introducing systems engineering, the process, and we'll talk about different modalities of how that's done, and we'll show some examples. So that the material sets the stage for the details that will follow in this course and in this textbook, as well as a number of other textbooks. So system engineering or engineering your systems, you need to be thinking from a broad perspective. You need to be considering the whole. So as a result, you oftentimes do not get as deep, although with the model-based system engineering tools that we have, you can actually do both, but you can be having a top-level way of seeing that, which is what system engineering is trying to cover at its core. So you need to be thinking about what must be done and how well it must be done. And so all of that has to be considered first, and then you can be thinking about how it should be tested. And so that's going to be important. You need to have a clear focus on the system's objective. And then in terms of design and integration, first for design, you want to start with the super subsystem. Have the top level way of looking at it, create those block diagrams and how they're related. You want to migrate towards subsystems and components. So you start with the big picture and then you go towards the details. So once you have the design, then you do the integration. We'll talk about something called the system engineering V. So you start with pieces and build to a system in its final environment. So the design, you go into more and more detail that's going down the V. And then for integration, you build the pieces, build to subsystems, and to the system sensor, you go up the other side of the V, is which we'll be showing. So as I'll be doing in this course, I'll be mentioning the various textbooks that we have that we're considering part of our complement of material. And so now we're going back to the practical guide to system engineering, to SysML, sorry about that. And so this is a diagram that may be helpful for us to be considering the system specification and design process. So they need to get to the stakeholders' needs, and so that's important. And so once you have it, then you need to be starting to formulate the documents, the database, which is more thinking in terms of what it is for SysML that capture what is that you're trying to do. You then, with those system requirements, you can be figuring out the system integration and having a system solution. But the thing is that you need to be doing is you need to come down to the lower level, the component requirements, and do the design and implementation and test of those. And that's going to be reflecting back into design feedback that maybe how are you going to best come up with a functional type of architecture that's going to work. Then when you have the verified components, you can be doing that system integration and test. And finally, having the integration and test feedback is important, because maybe the way you've architected the system, although it may sound good conceptually, but when you actually do the implementation, there's issues. So in terms of the flow, you start with the stakeholders' needs. From that, you have the information to do the system requirements, and then you could start to push down to lower levels for component requirements. And system engineering is a multidisciplinary problem that requires a lot of different things to happen in parallel. And so you can be thinking of the way that you're going to be organizing your team structure. And so you have the system engineering management team. So that's going to be important. And then you have these various other teams, the requirements, the architecture, the analysis, the integration and test. And so here is just an example of a typical multidisciplinary system engineering team that is constructed when you're trying to do a complex systems of systems development process. There's a lot of engineering standards. And once again, this is from the practical guide to SysML. And so we have the different process standards of the modeling methods, architecture descriptions and framework, modeling and simulation standards, and then we have the meta models and data exchange standards. And so we're going to be delving into the SysML as part of a model and simulation standard. So that's going to be the thing that we'll be focusing on. Booty, in our main textbook, he focuses a lot on IDEF0. We will talk about this a little bit, but that's really not going to be the focus. That's has a little bit of a different set of uses. And so we're going to be focusing more on SysML, so you can keep that in mind. You may get exposed to the different architectures and frameworks. DODAF, if you're working in the DoD, for example, that is a common framework, but there's other types of architecture description frameworks, MODAF, for example. And a lot of other information that is here, but I'm not going to talk about it in detail, but just to give you an idea, there are various engineering standards that are used in a lot of different areas in system engineering. So how do we start to create a systems model? And so we need to talk about, well, what is the overall capability, the mission that is meant to be done by a system. And so this is where we start to conceive of this model-based system engineering. So we have requirements and various specification documents, but here we have this engine where we actually develop a model. And so we actually have a couple of different types of views that show aspects of what that design is. And we'll get into this more detailed, and I have some other more focused lectures on this. You have the structure, you have the behavior, where I have the requirements, and then you have the parametrics. And so these are the four main pillars. And then there's more specific types of SysML types of diagrams that you can create, all of that representing a database that's going behind that. We can be doing analysis, and so some of this gets into discrete mathematics. And so you can keep that in mind. And then there's various types of links to models, model-based mechanical, electrical, software, and testing. And all of that can be mapped into a SysML model and potentially some other things that would go beyond just using what would be done in a SysML tool, whether it be something like Cameo, Enterprise Architect, or Visual Paradigms, which is the one that we'll be using in this environment for this academic setting. So I mentioned the system engineering V, and so this is the first time where we're seeing that. And so here you need to come with a conceptual design. You gradually get into more details, and then once you have this this detailed design, it makes sense, and you're able to build it. Then you actually do the building, the integration, the testing, and moving on your way to manufacturing and movement into operation. So this just gives a temporal view of the system lifecycle. And there's a lot of other things here, including the retirements. So you design, you build, you deliver, you operate, you maintain it. There's a potential for refinement, and eventually there's the retirement. In terms of the what is the cost versus time, and so we can see how what can happen initially, that there isn't that much cost that is laid out for a system. But then we have this huge commitment that, and when we get into the execution, once we actually have gotten a design, and now we get into the manufacturing process. And if you're not careful, there can actually be a huge impact as if there's a change in the design further later down in the temporal time frame of what things are done. The amount of cost it would take to fix the design is important. Model-based system engineering is something that can be helpful for that. And so this is the reason why engineering a system needs to be done well early, because when you start to do this cost commitment, you don't want to have significant overruns, or maybe having the schedule being broken as well. And those are often very tightly coupled. So from Booty, there's a lot of different sample definitions of systems engineering. I'm not going to be reading this, but you can either pause this and read these in detail, but just to give you an idea, and some of these are getting a little bit dated, but it gives you an idea of what are the definitions of system engineering. So let's think about that. System engineering is a multidisciplinary approach to transform a stakeholder's needs into a system solution. System engineering is a key practice to address complex and often technologically challenging problems. The process includes activities to establish top-level goals that a system must support, specify system requirements, synthesize alternatives. You need to have a phase where you'll do something called an analysis of alternatives, evaluate those alternatives, allocate the requirements to the components, integrate the components into the system, and verify the system requirements are satisfied. It also includes essential planning and control process needed to maintain a technical effort. So for definitions, engineering, this is a discipline for transforming scientific concepts into cost-effective products through the use of analysis and judgment. And for engineering of a system, or system engineering, this is engineering discipline that develops, maps, matches, and trades off requirements, functions, and alternative system resources to achieve a cost-effective, life cycle balanced product based on the needs of the stakeholders. And here we come back to the system engineering V again. And so we've already seen this, and this is just another view from Booty of how this actually works. So you come up with a design, you get more detail in that design, then you're ready to actually do the testing, the assembly, the integration and qualification of your system. So there's a lot of different decisions that need to go on through the whole process of system engineering in a life cycle. So you have the conceptual design, the preliminary design, the full-scale design. And so this is working down the system engineering V that we have there. And then we get into the moving our way up, the integration and qualification, and then the product refinement. So that's once again going up this side of the V. I won't read through all of these, but as we go through this course, you're going to be seeing how we're going to touch on a lot of these, and you may want to come back and reference this table here to be thinking about those types of questions that come up. There's a lot of different types of expertise required on a system engineering team. And so it's not all management, but you need to have management. So a lot of times the system engineering and program management are tightly coupled. And so we're seeing a little bit of that here. You can be thinking of the system engineering process. You have the stakeholders, and the stakeholders are going to be engaging with management and system engineering. But then you need to have the people who are actually building stuff. So the technologists, the engineering disciplines, and you need to have the modeling and simulation analysis. And so there's a concept of something called a digital twin in model-based system engineering, where you're creating a model. And so as you're going from an idea, a concept, to a more detailed design, you have this other modeling framework that you're playing against that can be helping you to be reducing the cost impact that you might have. And we showed that chart earlier, trying to prevent cost overrun and schedule overrun. So you want to be characterizing the broader design problem. And so here is just a picture of what that might be looking like. There's a lot of different ways of trying to be figuring that out. And so what exactly is a problem? Maybe the problem needs to be iterated a little bit, and you want to be thinking about how that can be sustained. That may be another aspect of the problem. Then you come up with a potential development systems. That's important. And then because of the modeling, there's meta type of data and concepts that we're thinking about. And so that's also going to be part of what we're trying to be thinking about. So you want to be designing the problem. You also want to be defining interfaces of what is within the realm of your control, what you need to work on, and what is outside that still needs to be accomplished. So we're talking about model-based system engineering, but there's also this classical top-down system engineering that has been going on for a long time. And so with the system engineering V, it's on purpose that we see that this is looking very similar to the system engineering V before. We have the requirements and going from a top level concept to more details all the way down to the component level. Then we start to do the testing and the verification as we move up. And so you have a companion, the system definition to the system sell-off document, the verification, validation, and assembly. And you can be seeing those comparisons as you work down to the details of the design, and its companion with the integration and test. So there's other types of models that you can be using for the system engineering process. And so here is a waterfall example. One of the things this is highlighting is the iterative process that can go through that whole process before we complete that. And so that is another useful. There's also the spiral method. And so we gradually get more and more complexity as we cycle through those spirals. And so that could be something that we can get at. So we have some initial operational concept, and we get more and more detail as we go through each spiral, as we go out to more detailed implementation and understanding of what we're trying to accomplish. Okay, earlier on, we had a chart that was trying to show the different modalities that was based out of our practical SysML textbook, but from Booty, it also talks about the modeling approaches. And so there is structured designs, and this is where this IDEF0 comes up, and that is a huge focus of what Booty has. But like I said, we're going to be focusing more on SysML. And then thinking about a framework, DODAF is a common framework that is used. And so here is an example of that. You can have operational views, system views, and technical standard views. And so these are the types of things that would be part of that architecture. So the short of it, there are a lot of different ways that you can be modeling a system. And part of this will be as you get experience, as you get exposed to different things, and what your customers or stakeholders are asking for, there may be some rigor that is forced upon you that you would be using. Well, let's show how we got to SysML. And some of you might be familiar with a unified modeling language. And these are the diagram types that were there. And initially, doing system engineering was leveraging what is done in UML. And UML is very closely connected with software engineering. If you've ever done some software development or software programming in one language or another, say like Java or something like that, you would see like having a class diagram would be something that would be quite common. And so we're going to see how this then starts to boil into what we have for SysML. And so in UML, we have three categories of structure, behavior, and integration diagrams. In SysML, we changed that a little bit. We have structure diagrams, behavior diagrams, integration diagrams, and requirements. And so if you click back and forth between these, you can see that some of them aren't so relevant for a system engineering type of construct. And so some of them are taken out. There are a variety that still are left here at class. It's renamed a block definition diagram. And there's also another one of those that gets more detailed, and it's called an internal block diagram. And we will be going through each one of these as we progress in our course, as we actually develop a model. In terms of behavior, there's an activity, there's a state machine, and there's a use case. Those are the things that fit into that category. For integration diagrams, it's using this construct similar to UML. We have the sequence diagrams, and then we have this very important part of it for SysML is this requirements, which you need to be spelling out exactly what you're developing. So that's something that you always have to come back to in system engineering. So you start with an operational concept. You first have to come up with an idea, and then you'd be thinking about, well, how at a high level is it actually going to be played out? You then start to be figuring out, well, what are the functions that are there? And then you can be having a physical architecture that embodies what you have with that functional architecture. And so sometimes you might see different types of flows going from an operational concept, functional, to a physical architecture, and eventually get to an allocated architecture. You're coming up with a specific design that you agree to go forward with, and then you need to be defining your interfaces. So we'll be coming back to these again and again, but just trying to give you some kind of a conceptual perspective. So here is an example of a physical architecture. And so for a fighter jet, an F-22, the weapon system, you can see how there's three different parts that they're trying to highlight. You have the vehicle, you have training and support. You can see how the training and support aren't gone into in more detail here, but for the vehicle, we have a lot of different details that are focused on. And yet again, we go much more in detail with the avionics versus the other things. So it's not necessarily saying that these things don't have more definitions, but for now, we're just focusing on the vehicle and then mostly on the avionics system with this type of a view. So if we think about some other type of architecture, and so here we're not being specific, but just call it a weapon system, or you can call it whatever. And so we have the operational system, and so we have the avionics, and so a lot of that is there. But then we have a lot more of these details that talk about the integration, design and integration, manufacturing, training, deployment, refinement, and retirement. So we're getting into the life cycle for that whole system. So hopefully these diagrams are giving you some more insight into what exactly that is done. This is another view of the design process. I'm not going to go into this in very much detail, but you can just once again seeing how this flows. You can think of the system engineering V as you're going down towards more details. And so this is another way of showing how that could be conceptualized. So for typical requirements documents, you may see some variations in these names, but for example, a problem situation and mission element needs, you need to have a need statement, a problem statement. So that's going to be important. A SEMP, a system engineering and management plan, that is something that's going to be key. And since this course is more focused on system engineering, it's good that that's brought up early on. You can have a stakeholders needs requirement. And so this could be called by a variety of different things, capability requirements document, a CRD, or here we're talking about a stakeholders requirements document. So that's usually what's given to some company to be developing things. And then we respond with the system requirements, an SRD or a SysRD, as they're trying to show, label it here. And so this is, you're responding to what the stakeholder is giving you, but this is actually what you're on contract, and this is what's going to be the top level of your requirements tree, if you will. And then finally, how are you going to validate those requirements? That's going to be something that's going to be critical, because you have what the requirements are, but then you have to be showing, well, how do we validate each one of those requirements? And there's different modalities in which requirements can be verified. So here's comparisons of the relative cost to fix. And so this is a focus on software, and some of the things that Booty focuses on is a little bit more software centric, but not always. But you can see how there's this tremendous exponential growth in the amount of cost it takes to fix errors as you go along. And so here is an example of 1,000 times if you're already in the testing phase that you didn't find it, versus if you get it early on, maybe just in the requirements phase, you just fix a line of code, you get into the design phase, it's going to be an order of magnitude greater, and it goes on and on and on. So those are some things that should be considered in terms of the impact of not catching something soon. So this is just a pictorial example. This is more going towards this, what's called this IDEF0 block approach to capturing what they're calling in general an ABC system. And so I'm just going to have a couple charts that talk about the development, the manufacturing, deployment, the refine and use, and then the use and retirement. We won't be using the IDEF0 in detail, but I'm just going to walk through this as we see. So first of all, we have the stakeholders are involved in this process. We're beginning to do the development to come up with a concept and then have something that is clear what exactly we're going to accomplish. Then we get into the pre-initial operation capability period. And so here we do the manufacturing. And so you can be thinking of the system engineering V, you're coming up that system engineering V. And so now we have a lot more details that we're getting into the deployment. There needs to be a training component so that people know how to operate the system. Then we get into, okay, we're no longer doing any development. It's been deployed. Now we just need to do the refinement and use and training for operation. You're just in the heart of the matter for operation. So that would be the third phase. And then we get into this last phase is where we're no longer thinking about upgrading. We're just trying to write it out as long as it's cost effective and functionally performing well enough to maintain before we actually go into a decommission and retire. And so that's just the 4 levels, one way of considering what it would be like for some arbitrary ABC system. So Booty talks about a lot of other different types of models. And so you can be thinking about the design and integration cycles. And so you can have the core cycle of doing the realization of stakeholders' needs, following the requirements, developing the design, and then you have the verification. So that would be a couple things that we're seeing here. So this is like in these types of loops. And I know with the colors here, it's probably really hard to see some of these lighter colors here. So we have the design and integration cycles. Then we have the management cycles where we have the technologies and external resources cycle. And so this is where decisions have to be made. Well, okay, what technology are we going to use to meet the requirements? We have the controlling where we're doing configuration management to making sure that everything is documented properly. And then we have strategic, the check cycle. And so you have management, constant monitoring of the product development to see if there's anything that's missing that maybe needs to be revised and reported. So that's just another example of a way that you can be thinking about. I mentioned this earlier very briefly, but now this tries to show you over 2 slides, the temporal view of how you actually do life cycle modeling and what's there. So you have the concept, the development, production, utilization, and retirement. So this is a general way of looking at it. And so this is using standards from ISO, IEC, and IEEE. So those are a standard between those 3 bodies. And so that's a generic way of doing it. You have a typical high-tech commercial system integrator. And so you have the study period, the implementation period, and the operation period. So that is a slightly different point of view. And then you have a typical high-tech commercial manufacturer. So this has the same comparison for the system integrator. A system integrator, they don't necessarily do all the details. A commercial manufacturer could be one of the players that's would then report to a commercial system integrator. So those are some things in terms of a couple different more generic life cycle models. And here we have some specific examples for parts of the US government. We have the Department of Defense, NASA, and the Department of Energy. And so you may have experience with one or more of these. And if you don't, that's perfectly fine. Over time, you'll start to be seeing that. And we see that there's these different milestones that they have with these little inverted triangles. And so you have phase A, B, C for the DoD model, the initial operational capability, and the final operational capability. So that's what we have there. NASA has a different way of conceptualizing their milestones. They have the formation, you know, the approval and implementation. And then the Department of Energy has something, they have the project planning period, the project execution, and the mission. And so those are just a couple things to be thinking about. So going up at a higher level again, to think of the 5 major functions of system engineering. So you wanted to be defining the problem, and then you want to be focusing on the design. You develop the functional architecture. Function comes first, then you have physical architecture. You want to develop the allocated architecture. So this is where you start to nail down, this is the specific way how you're going to be doing it. And then you want to be obtaining approval and document those approvals, working with your customers, your management team, and folks like that. Here are just a couple of more detailed diagrams that talk about the detailed functions of a system engineering design. You have the design problem. And so we're going to walk that, you know, develop the functional architecture, develop the physical architecture, develop the allocated architecture, and obtain product and approval and documentation. So this reflects this diagram, but we have more details with these different blocks and these dotted lines that you may be able to see with the, depending on the resolution of your monitor, you can see that these are the more detailed functions that need to take place in each one. There's be a couple other examples that we'll show through this course, say like getting more detailed in the NASA model, but this is Booty giving more perspective on that. And for this is the functions of the system engineering integration process. And so here we have an input, the verification requirements and constraints for approved baseline. And then we have a couple of decisions that need to be taken place. If there's no deficiencies, then that's great. We can continue on. If there are deficiencies, we need to be figuring out if they're correctable, and then we slowly come back. If they're not correctable, then we need to see if there's some way of having a waiver, and we can accept as is for somewhere within the overall design that's being worked out. So for the integration process for the product system and its qualification system, here is just another diagram showing this. And so You may be seeing that there's some relatedness to each one of these diagrams. So you have a concept that's then formed into requirements. From that, there's going to be more detailed requirements that need to be figured out. And then we come up with the allocated architecture, and there's going to be various levels of the system component and configuration items. And finally, that's going to be feeding into the integration and qualification of the system. So there's a variety of different types of systems. So this might be helpful to be giving you a perspective and thinking about what is the domain area? Is it something that's complex or simple, relatively speaking? How complex is it what you're trying to do? I'm not going to go through each one of these. Is it closed or open? There's open source, for example, both on the software as well as the hardware side. Where are your interfaces? Does it need to have a high level of reliability? That's going to impact what you're going to be doing. Is it a human-centric, or is it going to be doing a lot of autonomous operation? AI, artificial intelligence is starting to have a more of a high impact on what you would be doing for a system. So I'm not going to talk about this in detail. This is yet another tool that Booty talks about. And so you can feel free to be looking over this and reading about it in the textbook, but I just left this in for completeness in these set of slides. So let's just finish up with this first detailed chapter. What is the value of system engineering in terms of value propositions? You want to be working out the problem and solution discovery. So this is it's a goal-seeking system that you have in systems engineering. There's a communication interface between the stakeholders and design engineers. The system engineer is going to be the boots on the ground for making that happen. There's the identification and solving of showstoppers. And so you first have to figure them out early and then come up with a solution or workaround. That's the value of system engineering. Error reduction. And so I've heard one person say is like system engineering is like insurance. You buy as much as you can afford. You want to be minimizing error reduction, find them early in both the design and the production. And then risk reduction is identify risk and then manage those risks and try and prevent them from happening as you go through the design process. All right, well, thank you very much. That's the end of this lecture.